that I gave you before the break. Starting on the pH scale page. You want to check it, make sure we're all on the same page. I can delete you. Okay, so on the pH scale page, these are my answers. Compare what you got with what I got. I know mine's messy because I just cranked them out this morning. Compare what you got with what I got. If you got something different, perhaps I made a mistake. Let me know. Hey, how are you doing?
Great, how are you?
I'm good. Are you feeling better? Going once. Yes, Luca. Compare their relative concentrations of H plus and OH minus ions. Okay. So that one is, so determine the pH values of milk and banana. Banana was a 5, milk was a 6. This is just the idea that as you jump whole numbers on the pH scale, it's like you're getting 10 times stronger or 10 times weaker. So acids are going to have more hydrogen ions. Bases, things that are more basic, are going to have more OH minus ions than something that's acidic. So a banana down here at 5 compared to milk right here at 6. The banana, because it's more acidic, is going to have 10 times more hydrogen ions. That's what it's asking here. And then because milk is acidic, but it's on the acidic side of the scale, but because it's got a higher number than bananas do, it's more basic than a banana, and so it's going to have 10 times more OH. If you move to the right, it's more OH. If you move to the left, it's more H+. So that's 5B. Any other questions, comments, concerns from this page? Going once. And concentration is just, that word concentration is just how much of something is present compared to something else. The example I like to give is like making, if you've ever made powdered beverages, we make powdered iced tea at home all the time. The stronger the beverage, the more concentrated it is. So, yeah. Okay, flipping the page. A continuation of those pH scale questions. This 6B is the same. The concentration of hydrogen ions in solution A compared to solution B. 6A was on the previous page, but that's, yeah, these are the answers that I have for this one. Comments, questions, concerns. Compare what you got with what I got. If you didn't get, don't just copy. Do go back and do. You don't need to copy because I am, like, this is all being recorded. It'll be part of the video for today. You can go back and check once you've actually done the homework. And then the question down here at the bottom is, rather than labeling it all on the pH scale, cramming all of these answers in on this little line here, I just wrote down, based on the clue, I wrote down the approximate pH value for each of these clues. So seawater would be, if it's the same as egg, seawater would be an 8, which means seawater is slightly basic. Drain cleaner would be a 14. Pop is a 3. Blood's it says slightly more basic than pure water, so between 7 and 8. If you said anything between 7 and 8, I picked 7.5. Soap's a 10. Saliva is a 6. So your spit is slightly acidic. Black coffee should be a 5 on the scale. Malic acid, or the apples, should be a 3. Normal rain is slightly more acidic than milk, so that should be anywhere between 5 and 6. I said 5.5. So normal rain is slightly acidic. Seawater is slightly basic. Pure water on its own is going to be a 7, perfectly neutral. Orange juice is a 3. Battery acids is 0. Battery acids, a terrifying little compound. Comments, questions, concerns on anything from that page? Going once, twice, thrice, sold. Okay, cool. Then flip ahead, pH indicators. It was just using the indicators that we've talked about to answer a bunch of questions. So here are my answers to this page. Tomato juice is a 4 on the pH scale, so using this chart up at the top, if tomato juice is a 4, methyl red is going to be, methyl red will be red, methyl orange will be orange, it'll be between red and yellow. Bromethymol blue will be yellow, phenolphthalein will be colorless, indigo carmine's blue, litmus is red. The chemical name and formula for the acid in carbonated drinks is carbonic acid or hydrogen carbonate. Hydrogen, there's a bicarbonate. What's CO3? CO3 minus 2. It is carbonate, hydrogen carbonate. Be the chemical name. The acidic name is carbonic acid. Formula is H2CO3. And then 6 properties that lemon juice and carbonated beverages would have in common is just this page here. Those are the 6 things they would have in common, this whole column. Lemons and carbonic acid are both sour. Both of them will burn your skin, or could burn your skin. We don't see it happening overly dramatically. If I put lemon juice on your skin, you're not going to feel anything. But if I spray lemon juice in your eyes, you're going to feel a whole bunch of something different. If you've never had that happen to you, you didn't go to high school in the 90s. One of the things my buddies we didn't have smartphones, and so we made our own fun. One of the things my buddies used to do is they'd run around with orange peels or lemon peels, and like you squeeze them after you've eaten the apple or the orange or lemon. A fine mist of juice will spray out of them, which is flammable, first of all, which is cool. Also, if you get that in someone's eyes, it burns like crazy. So buddies would do that because that's what we did at lunchtime in high school. They will also slowly dissolve your teeth. People who drink a lot of carbonated beverages over time, you're going to have because it's down here. Where is it? Because, what is it? No, it's this one. It's the dissolving away or the burning of your teeth away is what these acids will do. Indicator tests are going to be the same for lemon juice and carbonic acid. They're both going to corrode metal given the opportunity. They're both going to be conductive. They're both going to have a pH less than 7. They're both going to produce H+ ions. It's this whole column, which is why I said C acid table. To see a sample is going to be tested with methyl red. The indicator is going to be red because they both have the same pH. It's a pH of 3, I believe. Or is it 2? It's the pH of lemon. pH of lemon is a 2. And then 3 required you to do a little bit of Googling. I don't expect you to know the answer to 3 on your own. You just go look. I found 2 this morning. There was a list of them that I found when I Googled natural acid-base indicators. 2 of them are red cabbage. Well, that's one of them, red cabbage. It's red in an acid, it's purple when it's neutral, and it's yellow as a base, which is interesting. And then turmeric, which you may find in your spice cupboard. Is going to be yellow if you put it with an acid or just water, something neutral. But it'll turn orange, or the thing I found also said like a reddy brown. If you put turmeric into a basic solution, it won't be that golden yellow anymore. It'll turn kind of an orange or red brown. And there was a bunch more on that list. I think there was 5 or 6 other things that you could have included. Did anyone find a natural acid-base indicator other than red cabbage or turmeric? Did anyone do their homework? Shame. Come on, guys. Or maybe you all found the same ones I did. More on the acid-base indicators. Take a look at this page here. These were my results. That's the whole page. Compare what you got with what I got. It's just looking at, it's comparing the pH scale diagram with the acid-base indicator diagram, and then identifying a whole bunch of things about all these different compounds. Compare what you got with what I got. Don't assume that if you got something different than I got, don't assume that I'm right and you're wrong. I just cranked it out this morning and mistakes happen. Again, you don't need to copy it out. It'll be in the video after you've had a chance to go back and do your work on your own. Comments, questions, concerns, going once, twice, thrice. Am I good to flip, or are we still comparing? You're quiet on a Tuesday morning. Okay, sold. And then this I added to your plate yesterday. This is just the table of acids and bases and their properties. The definition of an acid is a compound that produces hydrogen ions. The definition of a base is a compound that produces hydroxide ions in solution. The pH is going to be less than 7 for the acid. The pH is going to be more than 7 for a base. In the formula, you're looking for hydrogen present in an acid, an OH present in a base. Production of ions is the same, H plus and OH minus. Both are conductive. One tastes sour, the other tastes bitter. Acids will burn you. Bases will be slippery and they'll burn you. So it's fun, but it's burning. Examples, I've given you 8 of each, something like that. And then I just would put A's and B's down at the bottom here for identifying whether these things are acids or bases. You should have found that going A through L, acid, base, base, acid, base, acid, acid, base, acid, base, base, acid, is what you should have found going down that list. Comments, questions, concerns? Acids and bases. The one thing I'm not going to get you guys to do is name them. There are a whole bunch of acid-base naming rules depending on how many hydrogens there are and a whole bunch of other things. There's a bunch of acid, well, there's no base naming rules. The bases are easy, but there's acid naming rules. I'm not going to get you to do that. On the formula sheet, the periodic table paper that I gave you, if you look at the back page of that in the top right-hand corner, there are a bunch of commonly named acids. And if I give you a quiz or a test with an acid named there on the test or quiz and I don't give it to you, you pop up your hand and I will come around and I will give you the information you need for that. I don't expect you to name or know the names of acids or bases. Some of them will be easy. Hydrochloric acid is just HCl. But there's lots of them that aren't quite that straightforward. I'm not expecting you to memorize those. Okay. Before spring break, this little section here was called acids, bases, and salts. We haven't talked about salts at all, so let's talk about salts. Yes. You do what you got to do, Angel. Okay, when I say salt, or when I throw down a question like this, what do you think of when you think of salt? What do you think of? What enters your mind? When you think of salt, what do you think of? Food. Well, can you be more specific? Camparis, you're about to put your hand up. Oh, seawater. Sorry? French fries. Why do you think of French fries? So French fries have salt on them. What kind of salt? Or is there only one kind of salt? Table salt. So the common name for it is table salt. We've said it a few times. Does anyone know what table salt actually is? NaCl. So that is the chemical formula for table salt. Na is sodium, Cl is chloride. NaCl, sodium chloride. When you reach for salt on the table, this is what you're grabbing. Seawater will have the same kind of salt, NaCl. There's a sea called the Dead Sea, and the reason it's called the Dead Sea is it is so salty nothing can live in it. And as the water evaporates, the salt does not. The salt just stays, and the sea gets more and more and more acidic. The Dead Sea is in Israel, if I'm not mistaken. And so you can harvest salt in it, or salt from it. You go and you get big shovels full of water. The water goes away, the salt remains. What else do you think of when you think of salt? Sorry? Maybe I can't quite hear you. The stuff that melts snow. Does anyone know what kind of salt that is? Ooh, interesting. There's actually 3 apparently that are used. NaCl is one. So if you've ever been, I don't know where you live. I live in a condo building. We take turns salting the sidewalk, and so we get these big bags. They get delivered. We put them into one of those fertilizer things, and we take turns walking it down the sidewalk and spray salt everywhere. One of the things that it sprays is actually table salt, NaCl. That big bag is just table salt, rock salt, or coarse salt. But there are other salts that get used for snowmelt as well. One of them is CaCl2, so calcium chloride, and another one is MgCl2, magnesium chloride. We don't eat calcium chloride, we don't eat magnesium chloride, but those are also salts that are used to melt snow and ice. Is anyone here on a low sodium, like requires low sodium diet, or have a family member who's on low sodium? No, Himparsa is not low sodium. Okay, there's actually a food additive that if you need to be on low sodium, sodium being the Na part of Cl, and yet you still want to add salt to your diet, low sodium salt is actually KCl. So salt, there's a bunch of different things that are known as salt. You only can eat really 2 of them, NaCl and KCl. Sorry, what is pink salt? Pink salt is NaCl. Why it's pink is a good question. I don't actually know. Himalayan pink salt. What is it? My daughter is a huge fan of this stuff. Interesting. So Himalayan serum, let's do this one. Pink Himalayan salt. My daughter is a huge fan of pink salt. Himalayan pink salt is between 96% and 99% NaCl. But NaCl, if you've ever, you've seen table salt, it's white. On its own, it's white. So it doesn't take much. If you were to add anything to it, it wouldn't take much additive to change the color of salt that's white and effectively colorless. So the reason why Himalayan salt becomes pink, and it's not a uniform pink. Like there's different. If you look at the individual grains, there are shades of pink in Himalayan sea salt, and the reason for that apparently is that there is so 96 to 99, the other percentage, whatever it is, so 4% all the way down to 1%, are these things. There's some calcium in there, which changes the color. There's iron in there, which will give you that kind of reddish color. There's zinc. There's chromium. There's magnesium. And there are sulfate compounds. So SO4 minus. I think it's -2. So the thing that gives, even though pink Himalayan salt is the same as sea salt, NaCl, there's a percentage in there, quite a low percentage of these other things. And lots of them you need. You need calcium in your diet to help you build bones. You need iron for your blood, zinc, chromium, magnesium. We need these things in small concentrations. And pink Himalayan sea salt is safe, but it's these other minerals that give us that salt its color. So if we're going to define this, salt is not just table salt. That's what I need here. A salt, the formal definition for a salt is this. A salt is an ionic compound. They're all ionic. So ionic means, if we call something ionic, what does it mean? It's a metal and a non-metal. So there's going to be a metal portion, there's going to be a non-metal portion. So a salt is an ionic compound, so metal and a non-metal, produced through the reaction of an acid with a base. Which is why we lump the discussion on salts in with the discussion on acids and bases. A salt is defined to be an ionic compound produced through the reaction of an acid with a base. And so we're going to go from here, we're going to look at 6 or 7 different reaction types. The first one we're going to look at is what's called an acid-base neutralization. So acids and bases neutralize each other. They come into contact with each other. And you've done one of these reactions. For those of you who got through the which solution is more acidic. You started with an acid, you added to it NaOH. You added a base to it until the phenolphthalein you added turned pink. So you wanted the NaOH to eat up all of the acid that was in there, to neutralize it. And then when you started to have a higher concentration of NaOH, then the phenolphthalein takes over and turns pink. So an acid-base neutralization is the reaction of an acid with a base. So let's talk about them. A neutralization. Neutralization. Should be one word. Is the name for a reaction between an acid and a base. When this reaction happens, the products are always, well, one of the products is always the same and the other one is always a salt. What are you going to get if you take an acid and a base and react them together? So let's do a bunch of examples. What's this unknown product here going to be? Well, I've got this. I've got HCl, and let's react it with KOH. This is your acid. It's got the hydrogen out front. This is your base. It's got the OH out back. And if we look at what's going on here, if I take my hydrochloric acid and I break it down, this is made up of a hydrogen ion and a chlorine ion. The hydrogen is positive, the chlorine is negative. So my acid, the HCl, when I put it into solution, these two are going to kind of break apart. They're going to float around together. My hydrogen ions and my chlorine ions are going to be present there. My KOH K has a charge of +1. The OH is the polyatomic ion. OH has a charge of -1. On their own, dissolved in water, they are totally content to remain. It's the meme I showed you before the break. It's the, what's it called? Distracted boyfriend meme. Without the distraction, the couple is fine. Without the distraction, the couple is fine. But in the presence of another compound, they're going to switch partners. What is the only thing other than the Cl- that the H+ could react with? the OH. Positives are always going to bind with negatives. And so the H plus and the OH minus, because H plus was with the Cl minus, it's not going to get back together with the Cl minus. Again, it's the distracted boyfriend meme. The H is going to combine with the OH to make what? It's going to make HOH. HOH is more commonly referred to as what? Well, when we have multiples, yeah, when we have multiples of the same letter, we group them together, we add a subscript. This is going to be H2O. H2O is water. When an acid and a base react, they will always, always, always make water. Every acid has hydrogen, every base has hydroxide. The product here that always shows up when you react these two things together is water. And then the salt will depend on what other pieces there were in the acid and what other pieces there were in the base. So the H2O has already been made. What's left over? Well, I've got K and I've got Cl. The charge on K is +1, the charge on Cl is -1. So when these two get together, what's their formula going to be? It's going to be KCl. So because KCl is the product of a reaction between an acid and a base, this thing's a salt. We got water and our salt present at the end of an acid-base neutralization. And this is always how an acid-base neutralization is going to go. It's always going to take the hydrogen and the hydroxide, make water, and then the remaining pieces are going to get together and make your salt. Which leads, if you stop and think about it, leads to some very interesting reactions. I didn't have to pick HCl and KOH. I could have picked, let's do another example right here. I could have picked something like HCl and NaOH. HCl is more, where do you find HCl? If I asked you to go get some right now, what could you do? It would be gross, but you could do it. Without leaving the classroom, where are you going to get some HCl? Impara, so you look like you know. What's the other name for HCl? Yes, commonly. Hydrochloric acid is also stomach acid. If I asked you to go get some right now, what could you do? If I asked you to go get me some stomach acid, what could you do? Throw up, yeah. So HCl, this is your stomach acid. It would be gross, but you could do it. And NaOH, sodium hydroxide. NaOH is quite a deadly little compound. Found in, okay. Also called caustic soda. It's one of the active ingredients in bleach. There are a couple active ingredients in it, but one of them is NaOH. Now, on its own, NaOH, also called caustic soda or lye, dissolve. We talked about it before. Have you seen Fight Club, the movie Fight Club? Has anyone seen the movie Fight Club? Okay, a few of you. They dissolve bodies in NaOH, in lye. Whole body, your body will be gone. Your body also produces stomach acid, HCl. When you take these two things together, what do you make? If you got an acid and a base, you take your stomach acid and you put it together with some bleach, what's going to happen? The hydrogen and the hydroxide are going to get together to make water. And the Cl and the Na are going to get together to make what? NaCl. So what have you made? You take your bleach, you take your stomach acid, you put them together, you're going to make water and table salt. This you could drink, this you could put on your French fries. It's weird to think about those active ingredients doing that. On their own, both of these things can do a lot of damage to you. Together, they're going to make salt water, which you could then boil off and add to your French fries. Yes, sir. Nope. You did it in glass. the lab that you guys did, which one is more acidic? You used HCl. HCl was this guy here. These were the unknown concentrations of HCl. You reacted it with sodium hydroxide, NaOH. You're sitting in the classroom, you added one to the other. If you hadn't added the phenolphthalein on its own is toxic. This I will never let you drink. This would be dangerous for you to drink. It will burn your mouth, it will burn your esophagus, although I would never let you drink this. But if you mix them together, you've made salt water. If I could be certain that you did it properly, yeah. Yeah. The thing that you, the lab that you did, that turned pink, that you had all the flasks on your desks, different things were turning pink. At the point just before it would have turned pink, the pH would have been about 7. You would have had the acid being completely neutralized with the NaOH, and that would have been a drinkable beverage. It would have been gross, because salt water is gross. The drops make it toxic. If you hadn't have added those, you would have had a drinkable compound there, yes. Weird to think about. And on their own, either one of these things will do a ton of damage. The NaOH will burn your esophagus, burn the inside of your mouth. The hydrogen chloride will do the same. But together, I mean, if you guys get your wisdom teeth out, your doctor will tell you to swirl this in your mouth. It's gross. Salt water is a disgusting beverage, but it's totally safe. Weird to think about. So I've got a couple more here. As soon as you recognize that you have an acid-base neutralization, the first product that you can always write down is what? Water in the form of H2O. So all of these, if you look here, the hydrogen out front means I've got an acid. The OH out back means I have a base. For this one, number two is a little tricky. It's one of the ones that you need to remember. The H in this acid isn't out front, it's out back. This is acetic acid, or acetate plus the extra proton. This is just vinegar. So I've got acetic acid and the CSOH. Here I've got H3PO4, so phosphoric acid and sodium hydroxide. And then I've got nitric acid and calcium hydroxide. As soon as you can recognize that you've got an acid and a base reacting together, the first product is always going to be H2O. No, we're making a skeleton equation to start. If I asked you to make a balanced equation, it doesn't matter that there's HO2 and H, you're still just going to make water. The H's and the OH's are going to get together to make H2O. If I asked you to balance it then, that would be where you'd say, okay, well, over here, I've got 2 hydrogens and an oxygen. Here I have 3 hydrogens and 2 oxygens. So you'd have to go ahead now and change the numbers out front. But when you're actually building the thing, water is always going to be H2O. And now we have to go back and figure out what the rest of the compound is going to be. So in this first one, the H2 and the OH2, those are gone. All of the hydrogens from the carbonic acid and all of the hydroxides from the magnesium hydroxide are involved in the making of water. So what else here is now left? I've got to put together the magnesium and the carbonate. And when we're putting these things together, we're going back to one of the very first things that we did this chapter. We want to build these formulas using magnesium and carbonate. So what do we need to find to be able to do that properly? When you're building an ionic compound, what do you need? We need the charges. So this is where, if you don't know them, you'd reference your periodic table and your polyatomic ion chart. There are clues though. Hydrogen and hydroxide always have a positive 1 and a negative 1 charge. So if I need, for example, if I needed 2 hydrogens here, then the CO3 has to have what charge? -2. If I needed 2 OHs here to balance the magnesiums, the charge on magnesium has to be +2. So when I'm building this, I label the charges on my ions, and then I put these things together. If the charge on here is -2 and the charge on here is +2, When the magnesium and the carbonate come together, what's that formula going to be? It's going to be MgCO3. Good. When the charges are the same, you only need one of each. Or you can swap, drop, and reduce. What would this next guy be? The H's and the OH's go to make water. I have this whole piece left here, and I've got the CS left here. It's going to be CS, CH3COO, you bet. And the name for that thing would be cesium acetate. You don't want to touch that salt, it's radioactive. Okay, the third one, I've got H3PO4 and I've got NaOH. The H3 and the OH are going to go into making water. What's left? I've got Na over here, and I've got the PO4 over here. What's the charge on those guys? Angel, what's the charge on sodium? I saw you look it up. That whole first column all has the same charge. Sorry? It is 1. So Na's got a charge of +1. PO4 has a charge of -3. So when you make the compound, or the salt now, using Na and PO4, what are you going to have to do? You're going to swap and drop, and you're going to get Na3, PO4, or sodium phosphate, which is used as a fertilizer. And then the last one here, say that again. Good one. Let's take a look. What's the charge on Ca going to be? The charge on Ca is going to be +2. What's the charge on NO3? So you're telling me the charge on there is going to be -1 then. Okay? So if you swap and drop, you're going to get Ca, and you're going to get NO3, 2. There you go. And now if I asked you to go back and balance this, you could. And it would be the same set of skills you've done before. We'd drop the line, we'd list the elements, you'd go count, you'd add coefficients out front to maneuver those, or to massage those numbers until they fit the way you want them to fit. Okay, so these are salts. It's a quick lesson, relatively speaking. What I'd like you to go now ahead and do, I've got a couple pages of practice for you. I want you to take a look at this page here, recognizing acids, bases, and salts. Some of them you're going to have to flip back for to find. Go back and take a look at the tables where I gave you common acids and common bases. I then want you to go and take a look at these. I want you to do the acid-base neutralizations. I've got A through H here that are all just formula writing. I want you to balance. I want you to complete all of them. I want you to balance the aces. So A, C, E, and G. I want you to take some time and balance those, just to review balancing a little bit. And then this one here, down near number 2, I want you to complete. You do not have to balance these guys. I want you just to give me, I just want the word equation for these. But in order to do that, you're going to have to go figure out what you just have to complete the word equations here. You have to be able to do that, you're going to have to figure out what sulfuric, acetic, phosphoric, nitric, and hydrogen or hydrochloric acid, what those formulas are. Build the compounds and then give me the names. You don't have to balance, but I want the word equations for those. I think that's plenty of time or plenty of things to do. We'll save this page for a chapter review. There you go. On your mark and set giver. These 2 pages. You bet. Acids, bases, salts, and acid bases or acid-base neutralization reactions. Okay.